Good day. In this lecture, we will be discussing nuclear chemistry and nuclear binding energy, focusing on how energy is generated from the nucleus. By the end of this lecture, you should be able to compare nuclear and chemical reactions, explain nuclear binding energy, and evaluate energy released during binding energy calculations. Now, nuclear chemistry deals with the changes that occurs in the nucleus of an atom. The nucleus contains the protons, which is positively charged, and the neutrons, which are neutral. These are collectively called nucleons. Now, the nucleus is extremely dense. To give you a perspective about its density, it is actually comparable to compressing hundreds of millions of cars into a very small volume. This indicates that the nucleons are tightly packed and strongly bound. In nuclear chemistry, there is a term called isotopes. Isotopes are atoms of the same element with different number of neutrons. For example, uranium has an isotopes such as uranium-234, uranium-235, and uranium-238. These differ in stability and nuclear behavior. For your carbon, we have four isotopes. We have carbon-11, carbon-12, carbon-13, and carbon-14. For hydrogen, we have three. We have your hydrogen-1, also called as your protium. We have your hydrogen-2, your deuterium, and we have your hydrogen-3, which is also called your tritium. Now, let's compare nuclear and chemical reactions. In chemical reactions, electrons are being involved and atoms are being rearranged. In nuclear reactions, the nucleus itself changes, often producing new elements. Well, most importantly, nuclear reactions involve much larger energy changes. Now, we also have a concept called nuclear binding energy. In this case, your nuclear binding energy is the energy that holds the protons and the neutrons together in the nucleus. It originates from what we call your mass defect. When nucleons combine, some of the mass is lost and it is converted into energy. Let's solve some nuclear binding energy problem using helium-4. For the first step, we're going to identify the number of nucleons. Helium-4 contains 2 protons and 2 neutrons, thereby containing 4 total nucleons. For the second step, we're going to calculate the total mass if the nucleons were free. For the mass of the protons, that would be 2 multiplied by 1.00728 AMU, which is the mass of the proton. And AMU in this case stands for atomic mass units. For the mass of your neutrons, that would be 2 multiplied by 1.00866 AMU. And we're going to add the 2. Combining them gets us a total of 4.03188 AMU. For the third step, we're going to calculate for the mass defect. In this case, the mass defect equals the mass of the nucleus minus the total mass of the free nucleons. So in this case, 4.00150 minus 4.03188, which give us negative 0.03038 AMU. This missing mass represents the mass converted into energy. For the fourth step, we're going to convert the mass defect into energy using Einstein equation E is equal to mc squared. First, we're going to combine or convert the AMU into kilograms. Then, we're going to multiply by the square of the speed of light. This gives energy in joules, which is negative 2.73 times 10 raised to the 12 joules per mole. If needed, you can also convert the joules per mole using Avogadro's number. Now, the negative sign here indicates that the energy is released, meaning that the process is exothermic. And this energy is what stabilizes the nucleus. To compare stability, we divide the total binding energy by the number of nucleons. The higher the binding energy per nucleon, the more stable the nucleus. Nuclear reactions release a tremendous amount of energy. For example, a nuclear power plant requires far less fuel than a coal plant to produce the same amount of energy. Nuclear energy also plays a significant role in global energy supply, contributing to a large portion of electricity in some countries.